Hi, my name is Larouche. I'm a postdoctoral fellow at Clemson University. I'm working with Dr. Sam Price. And today I'll be presenting some preliminary results from a project where we're looking at how differences in habitat structural complexities may lead to differences in optimal body shapes, and we're looking at this in ray-finned fishes. So one of the reasons that fishes are such a great model organisms is that they are certainly incredibly diversified. We're talking about somewhere around 30,000 species, which represents close to half of present-day vertebrate biodiversity. But they're not only diversified in terms of number of species, they're also very disparate in body shapes. So we can have more traditional fish shapes, so perch or salmonids are a good example of that. But we can also have very rounded morphology, such as lobsuckers. We can have very elongated forms, such as eels and their relatives. We can also have these laterally or dorsoventrally compressed fish, such as batoids or angelfish and their allies. And then we can have just weird stuff, such as seahorses, for example. So one of the things that's really interesting is to look at what are the factors that may be involved in all of this disparity of shape. Obviously, there are a lot of factors, but here today we'll be talking about one in particular, which is differences in habitat complexities. One thing that fish certainly all share in common is that they have to swim. And they're doing this in an aquatic environment, which is very different from what we're used to in terms of terrestrial organisms. Water is obviously much more dense, about 800 times more dense than air is. It's more viscous too, and so this generates resistance to movement. There's two main types of resistance that we call drag, one of which is pressure drag, which can be seen as the energy that needs to be invested to move molecules of water out of the way. This generates increased pressure at the front end and reduced pressure at the posterior edge of the fish, and this leads to turbulence, which represents energy loss that's not necessarily invested in forward locomotion. And then we have a second source of drag, which is friction drag, which is when water does not flow evenly across the body of the fish, again generating turbulence. One way to reduce both these sources of drag would be to have some kind of fusiform morphology, much like this torpedo that we have here. So we have tapering anterior and posterior extremities. These help to reduce pressure drag. And as we have this nice cylindrical body shape with smooth surfaces, and these help to reduce friction drag. And there's certainly a lot of aquatic organisms that have converged on this type of a fusiform morphology, whether it be in birds, penguins being one of these examples. In mammals, we have dolphins, and we even have some prehistoric reptiles that also use this fusiform morphology. So this considered, why is it that fish have not all converged on a fusiform morphology if it's so efficient in aquatic environments? And perhaps part of the answer is that habitats are not all equal. And one way that they differ is that they differ in terms of the structural complexity that can be encountered. So on the left, we have a habitat which is open water pelagic habitat. Obviously, there are no obstacles. And in this case, we may have fishes that have to travel for long distances between patches of food. And in this case, it may be advantageous to have this kind of fusiform morphology that we talked about that allows you to reduce the energy loss through drag. On the other hand, if we're looking at coral reefs, there are many obstacles that fish have to be able to maneuver around. And in this case, you may want to have a morphology that maximizes maneuverability as opposed to reducing drag. And one way that we know this is possible is by having this very deep body morphology, lateral compression, and the fins kind of inserted around the center of mass of the fish. And these models have been discussed as early as the 1920s based on biomechanical considerations. And this brings me to the research question that we're addressing here. So this was a research question that a team of undergraduate researchers came up with through a program that we have at Clemson University, which is called Creative Inquiry. So we had a team of undergrads, and the purpose was to teach them all of the different steps of the scientific process. So they were involved in reading the literature, coming up with a research question, hypotheses that they could test, and they were even involved in the data collection as well. So we collected data at the museum, took some of our undergrads with us, and collected morphological data on over 17,000 specimens and about 6,000 species. The next thing that we had to do is, since our question is about habitat complexity, we need to combine this morphological data with categorical data for habitats. And we chose to go after this problem first with a really rough approach where we compared what is the most complex habitat that fish can encounter. Well, it's probably coral reefs. So we compared coral reef habitats to other types of marine habitats. And you'll notice that I'm mentioning marine. This is because nothing really compares to coral reefs in freshwater environments. So from our data set, we only use the marine portion of it. And then we plotted or mapped all of these habitat characteristics on a pruned version of our phylogenetic tree, which in this case was provided by Roboski and collaborators from their publication in 2018. And what's interesting here is that you can see that there are multiple transitions to and from reef habitats. And that's important because it gives us evolutionary replicates for our analyses. And then what we did is that we have more measurements than the ones that are presented here, but since these are the measurements that we had clear predictions based on habitat complexity, what we used is standard length, maximum body depth, maximum fish width, and caudal peduncle depth and width. And if there's any fish taxonomists here, I apologize for the fact that it's a freshwater species that's actually represented, despite that I'm using marine in this data set. Obviously, we had a lot of size variation in our data. So we had fish that were as small as a little under a centimeter, going all the way up to about 1.5 meters. And so since we were interested about differences in shape and not differences in size, we size standardized our data. What we used is a variation of the log shape ratio method. So how this works is that we start by calculating the geometric mean of our traits. In this case, we use the geometric mean of the 3 traits that are most informative of general size, which is standard length, maximum body depth, maximum fish width. And then we divide all of our traits by that geometric mean, transform it using log transformation, and as you can see from the density distribution of our geometric mean, it's very similar between our reef and our non-reef taxa. Now we also used a series of ratios which are perhaps more informative on the general shape of the fish. So we used the fineness ratio, which relates the length of the fish to its cross-section. One way to interpret this is that the higher that ratio, that means that you're going towards more streamlined morphologies, eventually eel-like forms. If you go to the other end of that spectrum, you're going to get very rounded morphologies. And to address the cross-section of the fish, we calculated the depth to width ratio, which gave us an indication. If we have a ratio of 1, it's a circular cross-section. Below that, we're looking at dorsal ventral compression. Above that, we're going towards lateral compression. We did some phylogenetic PCAs, but based on a couple of practice runs, if I talk about this, I'm going to go over. So we're going to move on to the results of our phylogenetic ANOVAs. So we use phylogenetic ANOVAs to compare reef and non-reef habitats, or rather to compare our traits between reef and non-reef habitats. What we found for starting with body depth is that we have a significant difference between reef and non-reef. And as expected, we have deeper forms that are associated with reef. The other thing that I'd like to bring your attention to is the R-squared values, which may seem kind of low, but in this case, we can see that we have our reef and non-reef categories explain about 8% of the variation in depth, which at that macroevolutionary scale, when we consider that there's so many other factors that come into play to affect morphologies, is still quite an impressive amount of variation that's explained by that. Body width, we were a little bit surprised that that did not come out as significant, but we'll get back to that in a few seconds. Caudal peduncle depth and width, both of these variables came out as statistically different between our reef and our non-reef. And what we found is that our fish in having simpler habitats have more narrow caudal peduncles altogether. Fineness ratio, again, significant difference between reef and non-reef. And what we're finding here is greater fineness ratios in our non-reef habitats, suggesting that these fish are more streamlined. And depth to width ratio, we have a marginally significant result. And here what we find is that we have increased depth to width ratio for our reef species. And as you remember, we did not find a significant difference in width. So what this may mean is that it's not so much the width itself, but rather its relation to depth and width, which give us that indication of lateral compression. So to summarize these results from these phylogenetic ANOVAs, we do find that for our simpler habitat categories, we have these more streamlined shapes with tapering tails. And so this does suggest that in these habitats, what's important is to have morphologies that reduce drag, because these fish may have to swim for longer periods of time, so they perform sustained swimming. In our complex habitats, as expected, we have deeper body form that are more laterally compressed, and we know that this is thought to increase maneuverability because it reduces turning radius. As for the thicker caudal peduncle that we're getting with our reef species, this may be to promote stuff like fast start to evade predators, for example, where a fish may want to try to hide in a crevice within the reef, so it helps to have this thick caudal peduncle to transmit force to the caudal fin. And more importantly, what's interesting here is that we have these biomechanical models for which we had expectations, and we're seeing that these patterns translate at a very large macroevolutionary scale, despite the fact that there are many other factors that come into play, and that may affect morphologies. And for some of these variables, they actually explain a pretty large proportion of variation, which is contrary to what we might expect at that particular scale. So some of what we want to do in the future is, certainly we have this very complex reef category, which represents our complex habitats. However, in our very rough way of addressing this, for our simpler habitat category, it does encompass a range of different structural complexities. So one thing that we'd like to do is to focus on what is the simplest type of habitat that they can encounter in the same way that reefs are the most complex, and that would undoubtedly be open water pelagic habitats. The issue that we're having is that we have about 2,000 reef species, and pelagic, we're left with about 300. So what we're going to do is implement some kind of a resampling procedure in order to address this and test that relationship. And then the other thing that would be interesting, whether it be for our more complex habitat inhabiting species or our simpler habitat inhabiting species, would be to test this within a convergence framework. And on this, I'd like to thank all of our collaborators as well as our funding sources, and I believe I may have a little bit of time for questions. Yes?
It seems that a lot of how this will turn out depends on what species you choose to measure. Did you use some sort of randomization about what would be in the coral reef and what would be in the pelagic?
So for scoring our species for reef and pelagic habitats, what we use is the categories that we find on fish face. The actual species that we measured, those were conditional on the Roboski and collaborators tree. So what we made sure is we wanted to have this robust phylogenetic framework, and so we use the same species that they have on their tree. Thank you.